So this is just as a reminder. So for these questions, these people were taking the test in person. They were allowed to use calculators on questions 1 and 2, and they were not supposed to use calculators on 3 through 6. You guys are taking it at home, so no one's going to know. I don't know what the rules are. You are welcome to use the apps on your phone for calculators, even if it says not to. As long as you're not using anything else on your phone, it's going to be fine. There's supposed to be 6 free response questions, and you have 90 minutes to complete them. All right, so this was their question 1. So now your questions will be different, but honestly, they'll probably be somewhat similar. They usually have a table type question with derivatives and integrals on just about every exam. So this is question 1. It's got A, B, C, and there is part D on the next page. And it says as follows: the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Values of f of r for selected values of r are given in the table above. All right, so there's values in the table up there. And we got 2 more people here, so I'm taking attendance. All right, use the data in the table to estimate the derivative at 2.25 using correct units. Interpret the meaning of your answer in the context of the problem. All right, so for A here, we want the derivative at 2.25. And if you notice, 2.25 is right in the middle of these 2 guys. So one way we could estimate the derivative at 2.25, and I'm using the estimate, not the equal to thing here, is just the slope between these 2 points, because derivative is slope. So we could say, you know, we got this point 2.510 and 2.6, so it'd be 10 minus 6 over 2.5 minus 2. So that's 4 over 0.5. So that looks like 8. All right, now we need correct units. All right, so this is milligrams per square centimeters. So milligrams per cm squared. And on the bottom was centimeters, so per centimeters. So that would be 8 milligrams per centimeters cubed. All right, and then we are supposed to interpret this. So at r equals, because this is an r in here, 2.25, and it's in centimeters. The rate of change, because that's what derivative is, it's a rate of change of the, and what does F stand for? Well, it's the density of the bacteria. Yeah, let that in there. Density of the bacteria is 8 milligrams per centimeters cubed. cc's is usually what we use for centimeters cubed, but that's fine right there. So there's our answer for A. All right, and then we'll move on to B, and B is asking us to do, it looks like, a Riven sum to estimate an integral. So the total mass in milligrams of bacteria in the petri dish is given by the integral expression. Oh, this was for centimeters. Where did I get? Oh no, it is square. Okay. 2 pi times the integral from 0 to 4 of r times f of r. So that's different. There's an extra r in there. There usually isn't that. We want to approximate the value of that integral using write a Riemann sum with 4 subintervals indicated by the data in the table. All right, so let's see. If we're going to do that, let's see. We're going to have one interval here, so that'd be 1. Then we're going to have an interval from here to here. That would be 2. From there to there, that'd be 3. And then from there to there would be 4. All right, and the right side for this would be the 2, and then the 6, and then the 10, and then the 18. So we can say that the integral, or 2 pi times the integral from 0 to 4 of r times f of r dr is going to be approximately equal to, so we're going to have the 2 pi out front, and then we're making the rectangles. Now the rectangles don't just have a height of f of r, they have a height of r times f of r. So the r is going to be, at the right side, would be 1. So it would be 1 times 2 times the width. And the width is 1 minus 0, so there's another 1 there. So this is the height right there. This is the width right there. Height, width. All right, that's the first rectangle. Now the second rectangle is going from 1 to 2. So at 2, we're going up 6, but then times 2 because that's r. So we get 2 times 6 times the width of this guy, which is also 1, plus the next rectangle. So at 2.5, we're going up 10. So 10 times 2.5. And then the width of this one is 2.5 minus 2, so that's just 0.5. And then finally, the last one, we've got r times f of r, so 4 times 18. And then the width of this one is 4 minus 2.5, so that is 1.5. All right, now it's just a matter of working out that. All right, so you can work that out if you want. You don't necessarily have to. I think that's an expression you could just write as an answer, but you do have a calculator. This is a calculator section, so you could just type that into a calculator and write your answer correct at 3 decimal places or in terms of pi. Either one would be fine. Does it ask us to explain anything, just to approximate? All right, so there's our approximation. And if we do want to work that out, let's see, that's 2, that's 12. 2.5 times 5 is 12.5. 1.5 times 4 is 6. 6 times 18, I don't know why that off. That's 36 times 3 is, what is 36 times 3? 12 times 9, is that 96? 108? And then we're just adding those up. And then times 2 pi. So 110, 134.5 times 2 pi. So that'd be 169 pi, I guess, if my numbers work out. Somebody can check me. All right, part C. 296. Did I add something wrong? No, it's not 1. That was already 1. Yeah, so that times 2 would be 269. There we go. Yeah, I was just reading your number. There we go. That's why it's always safer just to leave it just like that, because if you're going to work it out, you could make a mistake just like I did when you do 2 times 1 and you got 1. All right, part C is the approximation found in part B, an overestimate or underestimate of the total mass of bacteria in the petri dish. Explain your reasoning. All right, so we have, let's see, it said it's an increasing function. So we've got some sort of increasing function, and we're using 4 rectangles. Not necessarily these rectangles, but and then we're using the right-hand side. So if we use the right-hand side for these estimates, we're getting this extra area. So it's going to be an overestimate since f of r is increasing. And we used right endpoints. Right? If it was increasing and we use left, then it would be an underestimate. If it was decreasing, we'd sketch a little graph like this and we just kind of think of it. You can do that on your own paper, but this is what we want to write. Like, since the function is increasing or decreasing, that's what's giving us whether it's a overestimate or an underestimate. And the graph helps to explain our reasoning, but you guys can't draw a graph on your digital version, can you? So you're just going to have to write a sentence. All right, so on to part D. So this is where it kind of kicks up a little bit. So the density of the bacteria in the petri dish from 1 to 4 is modeled by the function g, defined by this nasty guy here. I think this is where the calculator part comes in. For what value of k between 1 and 4 is g of k equal to the average value of g of r from 1 to 4? Well, the first thing I want to do is I want to find the average value. And average value is 1 over b minus a, so 4 minus 1, the integral from a to b of the function. All right, so I'm going to find that, and that's going to be my average value. And then we want to know, when is it equal to that? So then I would take this function and set it equal to g of r. And then I'd be solving. So that might involve, graphing and seeing where the 2 lines cross, or using a solver function on your calculator. But I'm going to evaluate this on the calculator and get an answer. And then I'm going to solve it using the graphing. So let's see if I can evaluate it on the calculator. So one thing I did at the very start of class is I figured we'd be using that function. So I stored that in y1. So I've got it there in y1. So now I want to find this. So 4 minus 1 is 3. So we want 1/3. So 1 divided by 3 times the integral. Remember, math 9 is the integral from 1 to 4 of, well, my function. Well, it's in here. I think there's a faster way to get to it. I don't remember what it is. I think it's one of the alpha things, but there it is. There's y1. And the variable I used was x because I don't have an r available. So if I work that out, there we go. Yeah, alpha calc. Yeah, alpha, and then one of these, somewhere up here gives us that real quick, I think. Alpha calc, really? Oh, there we go. Yeah, there it is real quick. All right, but there's what we want. So we want 9.87579. And we want to know when does that equal g of r. All right, so, well, go to y equals. And I'm just going to type that into my other function here, 9.87579 graph. And now let's see where they cross. Looks like they cross right there. That looks like that's between 1 and 4. So let's see if we can find where they cross. Second trace, 5. Let's move over closer to it so it'll be easier for the calculator to find it. So enter, enter, enter. There it is, 2.497. R equals 2.497. All right, did it ask us to explain anything? Nope, just for what value are they equal? All right, so no sentences needed. There we go, and we got the work. Everything we needed is there. Done. Hopefully that's right. I don't know. You can probably find answers to this online. All right, but on to number 2. So we only use the calculator for part D there. We probably use it for part C there when we're adding stuff up. All right, for t greater than or equal to 0, a particle moves in the xy plane in the position, oh boy, so parametric equations or vectors. You can think about them either way. So here's our x of t, and here's our y of t right there. For actually, that's velocity. So x prime, y prime. It helps to read. Position, we don't know. At time t equals 0, the position of the particle is that. So we have 1 point for position at t equals 0. So we're probably going to have to find another point of position. Find the speed of the particle at that time. Find the acceleration vector at that time. All right, so there's 2 different parts of this question. I don't know, they probably should have just made this A and B, but whatever. So the speed is, so remember the speed is the square root of x prime of t squared plus y prime of t squared. All right, it's basically just the Pythagorean theorem with those 2 things. So we want to plug in 1.2 for each of those, square it, and then add them up and take the square root, and that would be the speed. So let's see, that would be the square root of 1.2 minus 1 e to the 1.2 squared, quantity squared. Almost forgot that. And then we've got sine of 1.2 to the 1.25 squared. All right, so that's really just a calculator exercise at that point. So let's quit that. Second square root of parentheses 1.2 minus 1, which really is just 0.2, but I'm lazy. Second e raised to the 1.2 squared. All right, then we want to get down, close those parentheses, square that whole thing, plus parentheses, sine 1.2 raised to the 1.25 out of the exponent, close the sine parentheses, close the whole thing parentheses there, and then square that guy. And I think that's it. Right, let's try. 1.271. Remember, 3 decimal places is what we want. And let's see, did it tell us what the units were? No, it didn't tell us what the units are anywhere, did it? Like speed, like is it feet, inches, centimeters, whatever. But there's our speed. All right, for the other part, we wanted the acceleration vector. All right, well, this is the velocity vector. So to get to the acceleration vector, we just take the derivative of each one of those parts. So let's see, derivative of the first part here, we're going to have to do a product rule. So it's first times derivative of the second. So that's e to the t squared times derivative of the exponent, which is 2t, plus the second, so that's e to the t squared, times root of the first, which is just 1. All right, so that's our derivative of the first guy. And then we need the derivative of the second guy. So the derivative sign is cosine. We'll leave the inside the same, t to the 1.25. Then times derivative of the inside, which is 1.25 t to the 1 less exponent. So that's 0.25. And that is our acceleration. Might want to just write that that's acceleration and not just a of t. All right, and then we want to plug in 1.2. All right, so we're going to get, let's see, 0.2 e to the 1.2 squared times 2 times 1.2 plus e to the 1.2 squared times 1. I don't need that. Cosine of 1.2 to the 1.25. 1.25 times 1.2 to the 0.25. And now we just have to work out each one of these separately and get a number. And then we stop. That's all we need after that. All right. We actually might be able to just leave it like that, but I would feel better actually working it out. Times second e raised to the 1.2 squared out of the exponent times 2 times 1.2 plus second e to the 1.2 squared. 6.2466. I mean, you could round that and say 7, or you could truncate it and just say 6. Either one's fine. I just put the extra digit for the heck of it. And the other one is cosine of 1.2 raised to the 1.25 out of the exponent, close the cosine. Then we've got 1.25 times 1.2 raised to the 0.25. Lots of stuff happening here. 0.405. And this is our acceleration at t equals 1.2. And this was our speed at t equals 1.2. Whew, a lot of work for that one, huh? That's definitely the longest part we've had so far. Part B, find the total distance traveled by the particle over the time from 0 to 1.2. All right, so part B, gosh, what was the formula for total distance? Can you use derivative function on calculator? Yeah, you could. So yeah, you could type in, that would probably be smarter than what I just did, ddx of t minus 1 e to the t squared at x equals 1.2. That would work too, yeah. Much easier probably. All right, so total distance traveled. Let me see if I remember that. So that's the integral of the speed, right? Integral of the speed from 0 to 1.2. So we have this is already the velocity. So this guy squared. So that'd be, I'm just going to put a bracket. T minus 1 times e to the t squared plus sine t to the 1.25 squared dt. All right, so there's no way I'm going to try and work that out by hand. I wouldn't even know where to begin. All right, but I do know how to type that into the calculator, if the calculator will let me. So second, math, nope, just regular math, sorry. Math 9, there we go. Maybe I do, maybe I don't. I guess we'll find out. 1.2, and then we've got the square root. It might have been easier just to type this into like y1 and y2 at this point. The number of times we've got to type them in here. But let's see, we've got parentheses, x minus 1. So we're using x instead of t. We've got e raised to the x squared. And then we want to close the parentheses for the first guy and square that. Plus, then when we got the second guy, we've got sine. Oh, they already started parentheses. My bad. So we get x to the 1.25. Close parentheses for the sine, close parentheses for the whole thing, and square that. And let's see, our variable was x. And our answer is 1.0098. Obviously, if you wanted to, you could put 1.010 if you wanted to, or 1.009. Either one of those would be okay, or put the 98. That's even more better. More better. It's a thing now. Part C, find the coordinate of the point at which the particle is farthest to the left. Explain why there is no point at which the particle is farthest to the right. Did I put that on the next page? No, I didn't. I'm trying to fit all this in here, huh? I was ambitious on this one, I guess you could say. Boy, we just got shoes.
Something addressed to the people who used to live here. Amazing.
Wow, that's packages from people that lived here 5 years ago. All right. Find the coordinates of the point at which the particle is farthest to the left. Farthest to the left means just the x is the smallest. So like x of t equals a minimum is what we want. All right, so we don't care about what y is doing at all here. We're looking at x. So here is x prime. So what we would do is, well, it's not just a minimum, it's an absolute minimum. So when we find absolute minimums, first of all, we use the endpoints. Well, we're just going from 0 onward. So that means one of our candidates is going to be, oops, maybe not x, t. T is our variable here. One of our candidates is going to be 0. Maybe it starts off farthest left and just goes right. Who knows? The other candidates would be where this guy, x of t, x prime of t equals 0. So x prime of t, let's see where I can fit this in. X prime of t equals t minus 1 e to the t squared. If I set that equal to 0, all I'm getting is t equals 1. So my only other candidate is 1. All right, so now I can do a couple things here. I can either do a number line chart with my derivative and see, is it decreasing before and then increasing afterwards? And then this guy would have to be our minimum. And then we could just find that. Or we could actually find the position using this point that we haven't used thus far. All right, so we've already got the position at 0 is at -2. So x of t over here is -2. I have a feeling our answer is going to be at this one. All right, but to find that answer, we have to do a little bit of work. So the position at 1 minus the position at 0 is equal to the integral from 0 to 1 of x prime of t dt. So what ends up happening, this x of 0, this is -2, right? It's given to us up here. So we get minus negative, that cancels out. And we just subtract it over. So we just subtract 2, so -2. And then that'll give us x of 1. So we just have to work out that. Back to the calculator. So math 9. And we're going from 0 to 1. Definitely would have been easier if we typed these into y equals and just left them there. But x prime is x minus 1 or t minus 1. And then we've got e to the x squared. I think I've got it memorized by now. Dx. All right, so we can do this and then add 2, and then subtract 2, or just put -2 on the end here. -2.6035. Or that's -2.6035. There is the farthest to the right. All right, explain why, or sorry, farthest to the left. Explain, so farthest left. All right, and explain why there is no point where it's farthest to the right. So it's always going to be increasing after that. So x prime of t is greater than 0 for t greater than 1. So always moving right after for t greater than 1. Doesn't it ask the coordinate? So y value 2. Find the coordinates of the point at which the particle is farthest to the left. Yeah, I guess we might need the y value there too. That's a lot of work. Gosh, this was a rough one. All right, so if we want the y value there, gosh, y of 1 minus y of 0 equals the integral from 0 to 1 of y prime of t dt. Y of 0 is 5. So we're going to add 5 over here. And gosh, I feel like I'm going to sneeze. There we go. And we're going from 0 to 1. Yep, I'm allergic to these. And let's see, we've got sine of x to the 1.25. Close the parentheses there with x. And then we have to add 5 to it, so plus 5. So there's the coordinate 5.401. So we get the point is negative 2.603. 5.401 is the coordinate. Gosh, that's a lot of work. Whew. So maybe I should write this answer up here. It's probably under my picture. So there's the y value at 1. And then after that, it's always going to be moving to the right because the derivative is positive. If I had more room here, I would probably show a little more. I would do the sign analysis chart on the derivative and say the derivative is positive and so on. But I did, I guess, say it down here in this tiny little blurb. All right, but hopefully you got the idea of how to do that problem. All right, the next one, the top problem, as it's been called online. A company designed spinning toys. Spinning toys, they don't want to call it a top. Using the family of functions y equals cx times the square root of 4 minus x squared, where c is a positive constant. All right, so it's a number. The figure above shows the region in the first quadrant bounded by the x-axis and the graph of y for some c. Each spinning toy, or top, is in the shape of a solid generated when such a region is revolved around the x-axis. Both x and y are measured in inches. Good to know. Find the area, so area, not volume, of the region in the first quadrant bounded by the x-axis and the graph of that for c equals 6. Well, it's just going to be the integral from here to here. So first thing we need to do is find when does it equal 0. So let's see, y equals 6x times the square root of 4 minus x squared. We want to set that equal to 0. So we're going to get x equals 0 and x equals 2, or I guess negative 2. But it looks like 2 is the one we want right here. So, because it's positive. Otherwise, I think it goes backwards and does some weird things. Like I think it goes down and does something similar, but we're not caring about that. We're only looking at the positive first quadrant. So there's our answers there. So that means the area of that region would be the integral from 0 to 2 of 6x times the square root of 4 minus x squared dx. All right, now we got to try and integrate this. And we don't have the calculator anymore. Calculator is now dead to us. All right, now you probably, since you are going to be doing this at home, you could probably just type this into your calculator and get an answer. But if they don't see some sort of work, they're probably not going to give you a full credit here. So you want to do substitution. U would be the inside, and then du would be negative 2x dx. All right, so we've got a 6x, we needed negative 2, so negative 2, negative 1/2, and I can just pull the 6 out as well. So now the 6 is out of my hair. So here's my du, and this is the square root of u. So we're getting, let's see, that's going to be a negative 3 out front. I'm going to leave off the bounds because technically the bounds would change, and I'd have the square root of u, or u to the 1/2 du. So this would be negative 3 u to the 3/2 times 2/3, or over 3/2. So the 3's are going to cancel. Cool. So we're getting negative 2, and then we've got 4 minus x squared to the 3/2. And now we're going from 0 to 2. So now I put the bounds back on because I'm back in terms of x. So if I plug in 2, it looks like I'm going to get 0. 4 minus 4 to the 3/2 minus plugging in 0. I'm going to have negative 2. I'm going to have 4 minus 0 to the 3/2. So this guy here is 0. Those negatives are going to cancel out. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. Hey, That's a nice round area. Cool. 16. Whew. Part B. Isn't it 1/3 in front of the integral? No. So I had a 6 in here, and I just moved the 6 out front because it wasn't being part of my DU. And then I added in the -2 to match. So I'm putting a -1/2 out front. So -1/2 times 6 gives us -3. So I had -3 out front, not -1/3 out front. Yep, no worries. All right, part B. Is it not? It is known that for y equals that, the derivative is, oh, so they're already giving you the derivative. Cool, that was nice of them. For a particular spinning toy, the radius of the largest cross-section circular slice is 1.2 inches. What is the value of C for this spinning toy? All right, well, looks like the largest radius would be right around there. And they're saying that this length from here to here is 1.2 inches. And we want to know what's C. Well, this is going to happen at the relative max. So that means the derivative here is going to be equal to 0. So I want to take this derivative and set it equal to 0 first to find what that x value is. And then, I can find the C by plugging it in there and setting this guy equal to 1.2. Right? Because right now I'd have this guy equals 1.2, like cx times the square root of 4 minus x squared should be equal to that height, that y value. But I have two variables, so I can't really solve. So that's why I need the derivative part here. So I'm also going to say c times 4 minus 2x squared over the square root of 4 minus x squared is equal to 0. So I just want when the top equals 0, the c is going to cancel out. I don't need the c. So 4 minus 2x squared equals 0. So 4 equals 2x squared. Divide by 2. Take the square root. And we only want the positive answer. So we're getting x equals the square root of 2. So that means we can plug in the square root of 2 here. So now we're going to get 1.2 equals c times root 2 times the square root of 4 minus root 2 squared. So 4 minus 2. So we're getting 1.2 equals c square root of 2 times the square root of 2. Well, that's nice. Square root of 2 times square root of 2 is just 2. Divide both sides by 2. We get c equals 1.2 over 2. All right. Let's say we divide both of those by 2. We get 0.6 over 1, or 0.6. So there we go. What's the value for c? It's 0.6, or 6/10. All right, part C. Seems weird. We found C, and now we're doing part C. All right, for another spinning toy, the volume is 2 pi. Okay, what is the value of C for this spinning toy? All right, so volume means we've spun it, and now we want the integral. So if we're spinning this, again, around the x-axis, I should probably switch colors here. Green, haven't used green yet. So now if we're spinning this around the x-axis, this would be our radius, which is just the function y, which is this guy. All right, so the volume would be 2 pi, and we're just doing the dis method. So we're going from 0 to here. Do we know what it is? Yeah, 2. It's still going to be 2. So from 0 to 2 of our y squared. So our y is cx times the square root of 4 minus x squared, quantity squared, dx. And we want this to equal 2 pi. All right, so really the 2 pi's cancel out. It wasn't 2 pi, it was just pi, sorry. Pi times the square root. So the pi's are going to cancel out, and we're just going to get 2. All right, so now we need to square this guy and then integrate it. So if we square this, we're going to get the integral from 0 to 2 of c squared, which is just a constant and can move out front, x squared, the square root squared. Like that. So if I move the c squared out front, I'm getting the integral from 0 to 2 of x squared times 4, so 4x squared minus x squared times x squared, which is x to the 4th dx. This is a pretty straightforward integral. So if we integrate this, we're getting, let's see, 4x cubed over 3 minus x to the 5th over 5. And we're going from 0 to 2. And let's see, if we plug in 0, it's going to be 0. If we plug in 2, we're getting c squared. Let's see, that's 8 times 4 is 32 thirds minus 32 fifths equals 2. Now, I'm not going to try and work that out. I'm going to say c squared equals 2 over all that. And then c is going to equal the square root of all that. Right? That seems like kind of an ugly answer. Oh, well, I don't see anything wrong. Do you guys see anything wrong? I don't want to try and put those together. I mean, something would probably cancel out and simplify. We'd have it a 15 in there somewhere, but I'm not going to try and simplify that. All right. Boy, oh boy. You also got that? Okay, good. Part number 4 here. So we're halfway done now. Let f be a continuous function defined in the closed interval from -4 to 6. I think this is f here. Yep, there's f. The graph of f consisting of 4 line segments, so they're all straight lines, is shown above. Well, I stuck it below. Let g be the function defined by the integral from 0 to x of f. Okay. And what open intervals is the graph of g concave up? Give a reason. All right, so g of x, so this is part A, equals the integral from 0 to x of f of t dt. Concavity is the second derivative, so I'm going to take 2 derivatives. So g prime would just be f of x, right? Derivative of the integral just gives you that. So g double prime, I kind of messed up my g there, is f prime of x. So g double prime is greater than 0. That's when g of x is concave up. When f prime of x is also greater than 0, since they're equal to each other. F prime is greater than 0 when f of x is increasing, right? That's what the derivative greater than 0 means. I guess I really don't need the is there. When f is increasing. So whenever the function f is increasing, that means g double prime will be positive and g of x will be concave up. So we're increasing from -4 to -2, and then we're increasing from 2 to 6. So we'd say g of x is concave up on -4 to -2 and 2 to 6. If you use brackets instead of parentheses, that's fine. And my reasoning is basically that right there, because that's where f is increasing. All right, so there's part A. All right, part B, this is probably where it gets a little bit more fun. Let P be the function defined by P of x is g of x times f of x. Find P prime of 3. All right, well, the first thing I want to do is I want to find P prime of x. So that means I got to do a product rule here. So that's first times root of the second. So that's g of x times f prime of x plus the second times root of the first. So that would be g prime of x. All right. Now to find p prime of 3, that would be g of 3 times f prime of 3 plus f of 3 times g prime of 3. All right, so g of 3, I'm just plugging into this guy. So that's the integral from 0 to 3 of f of t dt. Make sure you're using t. F prime of 3 is just at 3. So here's 3. And what's the slope? Well, that slope is over 1 up 1, so that's 1. F of 3 is the value here. So it looks like we're down at -3. So this would be -3. G prime of 3, well, we've said g prime is just f. So that's going to be f of 3, which is already what we said was -3. So that's just 9. So we're adding 9 to the integral from 0 to 3. So the integral from 0 to 3, so from 0 to 3, what is the area under the curve? That's kind of nasty. So we've got this triangle here that's positive. We've got this triangle here that's negative. this goes up 4, this goes down 4. These two are going to cancel each other out because this is positive, this is negative, and they're the same shape. So really, we're just getting this little part right here. All right, that little trapezoid. So let's see, that's 4, that's 3, that's what is 1, it's negative. So let's see, we've got the average of 4 and 3, so 1/2 -4 plus -3 times the width there is 1. So that's -7/2 plus 9. There's our answer, I think. That seems reasonable because that would be 8. Yeah, -3.5 plus 9. Yeah, you can. So you could also say that is 5.5 if you wanted to, I guess. That also works. So that's -3.5. All right. Part C. Find the limit as x goes to 2 of g of x over x squared minus 2x. I'm going to just go ahead and guess that this is probably going to be L'Hopital's rule, because if I see the bottom here, if I plug in 2 there, I'm getting 0 on the bottom. So if I want to use L'Hopital's rule, I've got to split it up. So let's see, what's the limit as x goes to 2 of g of x? Is that also going to be 0? Well, that'd be the integral from 0 to 2. From 0 to 2, we just said this was the positive part, that was the negative part. They canceled out. So that equals 0. The limit as x goes to 2 for x squared minus 2x equals 0. So it's indeterminate. So I'm going to use L'Hopital's rule. Remember, we can't just say it's 0 over 0. They get mad at us in the AP exam if we do that. We have to write out each separate part. All right, so if we use L'Hopital's rule, so I'm going to keep going down here, we'd have it equals the limit as x goes to 2 of g, capital G, not lowercase g, g prime of x over derivative of this guy is 2x minus 2. If I plug in 2 to the bottom, no longer 0. I think it's fine just to say that. I don't think you need to write it out. I think it's okay just to say that. All right, so g prime is, remember, just f of x. We've already said that other places. So now what's f of 2? F of 2 is -4, right? From both sides, the limit there is -4. Here, if we plug in 2, we've got 2 times 2, which is 4, minus 2, we get 2. So we get -2. There's our answer. Not so bad. I thought it might be worse than that. Thought we might have to do it twice. Let's go with red here. Now part D. The average rate of change of g on the interval, or find the average rate of change of g on the interval. Average rate of change. So that would be g of 2 minus g of -4 over 2 minus -4. Mean value theorem, yeah, average rate of change. Does the mean value theorem guarantee a value c between -4 and 2 such that g prime of c is equal to the average rate of change? So in other words, does this equal g prime of c for -4 is less than c is less than 2? Well, we need a couple things. One, the conditions for mean value theorem was that g of x is differentiable on the integral from -4 to 2. Was it open or closed? I don't remember. I think it's open, yeah. And continuous. I guess that one was closed because we needed to have the endpoints for that one. Otherwise, we can't do the function. All right, well, is it differentiable? Well, the derivative of g is just f, and f exists. So yes, that's true. Is it continuous? Yeah, it's going to be continuous. It's just the integral of a continuous function. So both conditions are met. So the mean value theorem should apply. I know they want you to think that there's a problem here at this corner, but it's just the function for the derivative. If we took the next derivative, then it might be a problem, but it's fine there. So yes, mean value theorem applies on -4 to 2. And now let's find this actual function value. So we want g of 2. It's the integral from 0 to 2 of f of t dt. which we've worked out a couple times, is just 0, minus g of -4. So that's the integral from 0 to -4 of f of t dt over 6. All right, so what we're getting here is negative, because this is just 0, we get rid of it. And then we're getting the integral that's backwards. So if we want to switch these bounds, we get another negative out front. It's going to cancel out that negative, and we're going to go from -4 to 0 of f of t dt. And then we're over 6, so I'm just going to put 1/6 in front. All right, so now we just need that area from -4 to 0. All right, so let's say I've got a triangle, which almost came straight down. There's 2, that height is 6th. So it's 1/2 2 times 6. Plus I've got this trapezoid here that has a width of 2. And then the average of the heights. So the heights are 6 and 4. So 6 plus 4 divided by 2. So let's see, those 2's cancel and that cancels. So I'm getting 6 plus 10 is 16, 1/6 of 16. So 16 over 6, which is 2.5. Is that 2.5? No, 2.6. All right, it doesn't actually ask me to find C. It just says, does the mean value theorem guarantee that there is one? And if we look and see, okay, well, let's erase a little bit of this. And we're going from -4 to 2. So is there some value of this function where it actually hits 2.6? No, here's 2.6. Yeah, it actually it happens twice, right there and right there. So yeah, it does happen. All right, so that was D. Whew. I'm getting tired. How are you guys going to take this whole exam? I guess they do give you a break between the sections. We didn't take a break. All right, number 5 here. Let y equals f of x be a particular solution to the differential equation with initial condition f of 1 equals 4. It can be shown that f double prime of 1 is also 4. Cool. Write the second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 2. All right, so we've got 2 things to do. First, we need the Taylor polynomial. Well, the Taylor polynomial would be f of, and we're centered at 1, plus f prime of 1 times x minus 1 to the first over 1 factorial plus f double prime of 1 times x minus 1 squared over 2 factorial, which is just 2. So this would be the Taylor second degree Taylor polynomial. So p sub 2 of x is usually what we call that. All right, f of 1 is just 4. F prime of 1 would be plugging it into there. So if I plug in 1 there, like right here, ln of 1 is just 0. So I'm going to get 0. So this guy is 0. F double prime of 1, they told me is 4 already. Cool. So I'm getting 4 over 2. So that's 2 x minus 1 because it's centered at 1 squared. So I'm getting 4 plus 2 x minus 1 squared is the Taylor polynomial centered at, or of degree 2 centered at 1. Use the Taylor polynomial to approximate f of 2. So p of 2 is equal to 4 plus 2 times 2 minus 1 squared. So that's 1 squared. That's 2 plus 4 is 6. So we'd say f of 2 is approximately 6 based on our polynomial. All right, cool. That wasn't so bad if we remember Taylor's polynomial. Use Euler's method. I was thinking Maclaurin polynomials. Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 2. Show the work that leads to your answer. All right, well, whenever they ask me to do that, I start making a chart. And let's see, I got a dx, and then dy is dy dx times dx. dy dx is this. So I'm going to have y times x ln of x times dx. So I'm starting at the point I know. I'm starting at 1, 4. I want 2 steps to get to 2. So let's see, I'm going from 2 to 1, divide by 2. So I'm going to be stepping by 1/2. Going to be hard to make the chart in the app. Let's just hope they don't ask us to do that. you're just going to have to write the parts in. Like you'd have to write dx is 1/2, x is 1, y is 4. You'd have to write out this, just the work for this. So this would be 4 times 1 times ln of 1 times 1/2, which this is still 0. So we're getting 0 there. So I'm adding 1/2 to 1. So I'm getting 1.5. I'm adding nothing to y, still 4. My dx is still 1/2. So now I'm plugging in again. So I get 4, 1.5 ln of 1.5 times 1/2. Gosh, what is that? I hope they don't want us to try and work out the ln of 1.5. 2 times 1.5 is 3. So we get 3 ln 1.5. So I'm getting, right here would be 4 plus 3 ln 1.5. That's what I get. I don't know what the ln of 1.5 is off the top of my head. I could bring in the 3 as an exponent, but I don't know 1.5 to the third power either. So that's not helping me either. But that's a fine answer right there. All right, it's going to have ln's in it. All right. So that's A and B. What else do we have here? Part C, find the particular solution y equals f of x to the differential equation with initial condition. All right, well, cool. Something straightforward. And we don't forget that. So we got all the y's and dy's on one side, x and dx is on the other. So I'm going to move up the dx, move down the y. So dy over y equals x ln of x times dx. We want to integrate both sides. The left side over here is just the ln of the absolute value of y. The right side is ugly. All right, so I don't think we can do this just using normal substitution. I think we need to do integration by parts here. So if we're doing integration by parts, and we're going with, let's see, remember Liate? Liate. I think that was, so it was logs, inverse trig, algebra, trig, exponentials. So logs is the first one. So that's what I want to use for u. And then my dx, or sorry, dv is x, dx. So du is, well, 1 over x. Good, the log goes away. If we integrate this side, we get v equals x squared over 2. So we get this times that minus the integral of that times that. I guess I should probably put a dx there. All right, so that's going to cancel. That's nice. So the 2 can come out front. So I'm really just doing 1/2 the integral of x dx, which is x squared over another 2. So that's 1/4. So what I'm getting here is the ln of the absolute value of y equals x squared over 2 ln of x minus 1/4 x squared. So x squared over 4. Go ahead and put the c over there. We might go through multiple c's. All right, so now we want to solve for y. Okay, well, let's call this C1. Find the particular solution, y equals. Yep, so we want to solve for y. So we're going to take the e of both sides. So we're going to get y equals, and then I can bring down this c out front. Remember when we always change this c to just a different letter because it would be e to the c1 times that whole thing. So let's just call it c, e to the x squared over 2 ln of x minus x squared over 4. And now we need to solve for c. So now we use our initial condition. So 4 equals c e to the, you get points off if we don't label the c's right. I don't know if they're going to take points off for that, especially for you guys that are doing it digitally. All right, so we plug in 1 here, that's going to be 0. Plug in 1 here, we're getting minus 1/4. So we're getting 4 equals c e to the negative 1/4. So really c over e to the 1/4. Multiply that up over here. So 4 e to the 1/4 equals c. So it looks like y equals 4 e to the 1/4 times e to the x squared over 2 ln of x minus x squared over 4. I mean, you can bring the 1/4 in here and just say plus 1/4 if you want, but that seems like extra work to me. I'm done. There it is right there. All right. Who's calling me? And finally, numero 6. All right, so we're going to be done in about an hour here. And we had 90 minutes. The function g has derivatives of all orders for all real numbers. Cool. The Maclaurin series for g is given by that. All right. On its interval of convergence. So it only converges for some point probably, or some interval. State the conditions necessary to use the integral test to determine the convergence of this series. Use the integral test to show that that converges. All right, so for the integral test, let's see, we had a couple conditions. So we needed that, let's see, the first thing we needed that the thing in here, 1 over e to the n is greater than 0. That checks out. 2, we need 1 over e to the n to be continuous. That checks out. And 3, we needed it was decreasing. I think we need that it was decreasing. And that also checks out. All right, if you want, you can take derivative. Let's see, we'd have e to the negative x, we could say, and that would be negative e to the negative x, which is always less than 0. So it's decreasing. All right, so there's our conditions for the integral test. They do work out, it is decreasing. And it says use the integral test to show that. So now we'll be integrating, let's see, we're going from 0 here. So 0 to infinity of 1 over e to the x dx. And if this converges, then that series converges. All right, so we just need to integrate this. So I'm going to rewrite it. E to the negative x dx. So technically what I would do is I'd be like u is negative x, du is negative dx. So I would just put a negative in here, a negative out there. So I'm getting negative the integral of e to the u du, which is just negative e to the u. Why am I putting negative up there? Which is negative e to the negative x from 0 to infinity. All right, now, oops, I probably want to not write it like this though. I probably want to write it as the limit as b goes to infinity and put b up here and b there and b there because it's an improper integral. All right, so we're going to get limit as b goes to infinity of negative e to the negative b minus negative 1. I think if we plug in 0, we're getting negative 1. All right, so now as b goes to infinity, this is basically negative 1 over e to the b. So this whole thing is going to go to 0. So we're just getting 1. So in other words, this integral here, this integral converges. Therefore, the sum from 0 to infinity also converges. That's what the integral test tells us. There we go. Got it. All right. Now, honestly, if I was asked to just find if this converges, I would say this is 1 over e to the end. I'd say it's geometric, where r equals 1 over e, which is less than 1. Therefore, it converges. Done. But they said we had to use the integral test. All right. Now they want us to use the limit comparison test with the series that to show that this series converges absolutely. All right. Well, if we want to show that it converges absolutely, we probably want to take absolute values. So the absolute value of that series equals 0 to infinity. Actually, take the absolute value inside. Negative 1 to the n over 2e to the n plus 3. We want to show that it's less than 1 over e to the n. And this that we know converges because we just showed that it converges. Actually, no, we're doing limit comparison, not just comparison, sorry. So limit comparison, we're taking the limit as n goes to infinity of the absolute value of this guy. Sorry, I didn't need to do that at all. No, I'm not going to try and erase it. Over this guy. And if this just equals a number, then they both do the same thing. That's the limit comparison test. All right, so the absolute value is going to kick out that guy. So we're going to flip and multiply. We're going to get e to the n over 2e to the n plus 3. We're taking the limit as n goes to infinity. We're really just going to have the coefficients here. So this equals 1/2. Therefore, since this guy converged, this guy converges. And since it was in the absolute value, it converges absolutely. Check. On the comparison test, fun times. 2 more. Determine the radius of convergence for G. All right, well, there's G. Radius convergence meant we were doing a ratio test. So for part C, we're doing the limit as n went to infinity of that whole thing, or we could do geometric, but it's not quite geometric, so it doesn't work. So this whole thing in absolute value with n plus 1s over 2e to the n plus 1 plus 3 times this guy flipped over. So it's actually over that whole thing with just to the n. And let's see, we've got -1 to the n, x to the n. So the absolute values are going to get rid of the -1s. The x to the n plus 1 and x to the n are going to cancel, and we're just left with this x on the top. These two guys aren't going to cancel because that plus 3 gets in the way, but it is going to work out pretty nicely. So we've got 2e to the n plus 3 over 2e to the n plus 1 plus 3 times the absolute value of x. We want that to be less than 1. All right, we need to take this limit here, basically. So what happens with this n plus 1 is we can rewrite this as 2e to the n times e to the first plus 3, or 2e times e to the n plus 3. And then it's just the coefficients, because they're both e to the n. So it's 2 on the top, it's 2e on the bottom. So we get 2 over 2e, or just 1 over e. So we're getting 1 over e times the absolute value of x is less than 1. If we move this e over, we get the absolute value of x is less than e. And that right there is our radius. All right, so we solve for just x by itself. There's our radius over there, e. Part D. So we just needed the radius. We didn't need the interval, just the radius. Okay. The first 2 terms of the series g of 1 are used to approximate g of 1. Use the alternating series error bound to determine the upper bound of the error. Okay, that's not so bad. So the alternating series error bound is just the next term. So the first term is n equals 0. The next term is n equals 1. So the term that we're on now is n equals 2. That's the next term. And we just take the absolute value of that. So we're going to plug in 2 for n and 1 for x. All right, so we're going to have n equals 2, x equals 1, and we want the absolute value of that. So -1 squared, 2e squared plus 3. So that is 1 over 2e squared plus 3. That's it right there. That is the error bound. So like the difference between the sum and the sum of just 2 terms has got to be less than or equal to 1 over 2e squared plus 3. No, I don't think we need to, because we're not doing a Taylor approximation. We're just summing the series. And actually, this isn't, is this S sub 2 or S1? This would be 0 and 1. So this would probably be S sub 1, actually, because we're doing 0 and 1. I don't know. It doesn't matter what I write here, but this is the important part, what's over on this side. Yeah, alternating series error bound is just the next term. It's not asking for like the Lagrange or Lagrange error bound, which involves other stuff, which is the maximum value of the function on the interval and divided by the 2 factorial and then times the difference between the x value and where it's centered. So that's something different. So this is just the alternating series error bound, which is just the next term, the absolute value of the next term. All right. And that's all of it. Whew. How long did that take?